we're going to talk a little bit more about second order systems and about how we can shape them. So if we have a second order system that looks like this, then how we can do some analysis by finding what we call the natural frequency and the damping ratio. So I'll just define those terms for us right here first. So we have something called the natural frequency. Okay, and we denote it as an omega sub n. And this is this point where the system tends to oscillate. So for example, in an RLC circuit, the oscillation point where the impedance of the inductor and the capacitor, where they cancel each other out, that would be the natural frequency of the system. So where the system tends to oscillate. And we have another term, so that's the natural frequency. Another term called the damping ratio. And we denote that with, I'm really bad at the symbol, but we'll try something that looks like that. And we can use these terms to help break down our system. But right now, we have these terms and we have our system, for example, say it looks like this. Then how do we get between these two systems? Well, the natural frequency has to do with when there is no damping, it's just an oscillation. So if we look at our bottom here, the denominator, we know that if we have s squared and only a b, so if a is 0, then we will get some oscillation because we'll be on the imaginary axis. Our poles will be on the imaginary axis. So b roughly correlates to omega here, and then the damping constant comes into play with this a. So I'm not going to drive the whole thing. If you want to see the derivation, you can do it yourself or look in a book. But what we end up doing is rewriting this system. So this ends up looking like omega n squared, so the natural frequency squared in the numerator. And then we have s squared here. And then a will become 2, the damping constant, omega n s plus omega n squared. And we're going to do a little bit more analysis, but essentially what we do is we understand these things, or we'll talk about them more, and we gotta force them into this equation. And we notice that it's like this omega n and this omega n, they're the same, and you can try to fit your equation into this form. But what if, you might have the question, what if I have another constant out here or something? So we have a constant alpha, or alpha, like this number does not match this. All you have to do is take this and move it to the front so it can become a scalar. So that's just to address that question. So if you want to force it into this form, but your top number doesn't match this, you can take out a constant. Okay? Okay, so say you can get your system into this form. And so next we will look at second order systems specifically and some of the common time responses that we have, so responding to a unit step, and some of the terms that we use to explain those systems. And second order systems are important because they're very well studied in the literature, so you can find lots of resources on them. And a lot of times if we have a more complex system, we're able to simplify the model into a second order system that's more manageable for us. So we won't spend too much time on that, but if you're interested in this, there's lots of good literature, the book that we use in this class, and many other books or resources. So we're going to assume that we have a system, a second order system, and it's second order because it has 2 poles here, so we have s squared, so we know there will be 2 poles here. And again, we're going to input our step function, so 1 over s, to see how the system reacts to a step input. Okay, and so there's a few different terms that we're going to use, and the first one is going to be for a system that has, it's called overdamped, an overdamped system. And so again, we're going to have our system here be the objective is to feed Valerie, and in order to feed her properly, we have to get the food to stay over time, stay at this value so that so this is our target value. And an underdamped system, it's a stable system, so it will go there. It just is really slow to get there. So you say go, and it tries really hard, but it's just really slow to get there. So this is like something that has a lot of mass. It's really, really, really hard to get there. And this is supposed to be a straight line, or a curved, well-curved line here. It just takes a really long time to get going, and eventually it kind of gets there. Maybe that's close enough, she can eat it there. But this is what we would call overdamped. And so here, if you remember our rise time and our settling time, we have a really slow rise time, really long rise time, and a really long settling time because we do not settle very quickly. Okay, so that's overdamped. If we look at the poles for this, see if I can draw them here, they tend to be on the real axis. So this is real, imaginary. There's also a really great diagram in the Nice book. So look at that if you need more examples. They tend to be on the real axis, but one is pretty close to the imaginary axis. So very slow to react, but eventually it will get there. That's called overdamped. Okay, the next one is the more opposite of that. It's called underdamped. And in this system, I'll try to use I only have two colors here, but you start and it goes, once you say go, it goes, but it goes a little bit over too much, and then kind of eventually we'll get close to where we're trying to go. So this would keep oscillating a little bit. This would be called underdamped because we're getting some of the oscillation in there, and it is eventually going to the settling point, but it's taking a little bit of time. So this would be called underdamped. And again, if you think about settling time and rise time, this settling time is just as long, it takes a long time, but the rise time is very short. So to go from here to here, right, 10 to 90% was very fast, but it just takes a long time to settle. And if we looked at the poles for that one, that would be in the imaginary, has some imaginary component. So maybe say about here. So we would still have some imaginary component, and it's relatively close to the imaginary axis here. So that's what that would look like. There's two more that we'll look at. One is called undamped, so not underdamped, but completely undamped. Oh my gosh. Undamped. And this is where you pretty much have only the sinusoidal component. So we'll do that here. So we get this and we just get some nice oscillation going here. Didn't quite draw it perfectly because I have to ruin our title here. But we just have pure oscillation that continues. And so this, I guess technically would have a high rise time, but it has no settling time. So it never settles. It just continues to go on. And this is what we called marginally stable before. So if we draw another version of our axes here, our real and imaginary, then we would have our poles directly on the imaginary axis. So we're just oscillating. It's purely sinusoidal. And then our last one, we're going to call it critically damped. Damped. And this one is what we want to have generally. So this one kind of goes up. It maybe does a little tiny bit of overshoot, but then goes right to it. Actually, I think there's very little overshoot. Just goes pretty fast. So this one has a very high rise time and a fast settling time, or short settling time. So this is kind of the ideal performance if we want things to move quickly. And for that, we have generally either two poles right on the real axis, or there's some other pole positions that could be ideal for what you want. But Critically damped in this case would be where the poles are right on top of each other and the real axis. So these are just terms that are important to know. So if you say, oh, my system's over damped, it means you need to, compensate for that. If it's under damped, you need to damp it a little bit more and change the position of the poles. Okay, so I'll just stop there for now, but now you should be able to understand when someone says the system is underdamped, overdamped, underdamped, undamped, or critically damped. You should know what that means.